Hi class, welcome back. Today we're going to discuss the bases other than E and its applications. This is 5.5, and what I mean by bases other than E, we mean the exponentials functions other than base E. We're going to discuss the definition of this exponential and how this relates to natural exponentials in one way or another, and define the derivatives and the um, and possibly the integral, how to integrate them as well. The objectives are to define exponential functions that have base other than e, differentiate and integrate exponential functions that have bases other than e, use exponential functions to model compound interest and compound and exponential growth. All right, let's begin by defining these exponentials other than e. So the base of the natural exponential function is e. That's why we call it the natural exponential. This is natural base can be used to assign a meaning to a general base a, such as what we're going to do it in the next definition. So the definition of an exponential function to base a: if a is a positive real number other than 1 and x is any real number, then the exponential function to the base a is denoted by a to the x and is defined by a to the x is equal to e to the natural log of a times x. Now, let me show you guys real quick how this two things are the same. So if I have a to the x, right, then a to the x is a to the x, right? Obviously. Well, what I can do is remember that we had a special rule that e to the natural log of anything will be the same thing, right? Of itself, right? These two we cancel each other out, so it's like not doing anything. So if I do that, then this still is a to the x. Now, because this is the natural log over here, then I can put that in to the natural x times the natural log of a, right? So that's still the same thing as a to the x. So I'm just doing sort of like a manipulation of the algebra of natural exponential, right? But the reason why we're connecting this, it will make more sense in a second. So hang in there. If a equals 1, then obviously we have 1 to the x, and this is going to be 1. So this is no longer an exponential. This is just known as the constant function, right? So that's why we are excluding a from being equal 1, because if it equals 1, then this is no longer an exponential. Remember that an exponential function has a specific definition, right? It increases exponentially, right? So we want to make sure that when we define the exponential, that it still has the definition of an exponential. All right, so just these are some familiar properties that we have discussed before. So here are a quick review. We have that these functions obey usual laws of exponents. For instance, here are some familiar properties. A to the 0 is 1, as anything to the 0 power is 1. A to the x times a to the y is equal to a to the power of x plus y. A to the x over a to the y is the same thing as a to the x minus y. A to the x to the power of y, then we have a to the x times y. All right, so one of the benefits of using exponential functions is the fact that we can model half-life radioactive samples. So it is convenient for us to use it specifically when we have half radioactive. So we're going to do that in the next problem. So when modeling the half-life radioactive sample, it is convenient to use 1/2 as the base of the exponential model. Half-life is the number of years required for half of the atoms in a sample to radioactive material to decay. So what this means is that when you talk about half-life, you're referring to usually like you're trying to find how long will it take for the material to decay to its half-life, meaning that it's only have half of its substance. For example, here they're talking about radioactive. Well, we know that radiation will decay over time, and so if you want to find the half-life of this, then you want to find out the time that we require for the radioactive to decay to its half a life. I mean, 50% of what it originally started with. So let's try example one. We have here a radioactive half-life model. The half-life of carbon 14 is 5,715 years. This means that it will take 5,715 years for carbon 14 to decrease to half of its substance, right? To half of its substance. So let's say you have a sample that contains 1 gram of carbon 14. How much will be present after 10,000 years? Now you might be thinking, wait, I can do this math because I know that if half-life it takes 5,715 years to do half-life, then if I have 10,000, that's just double that. Then it should just be 0. Well, it doesn't work like that, right? Because it's an exponential. This is type of exponential problem. It actually is going to work in a different way. So let's go ahead and try the problem. We know it's half-life decay. So we remember from algebra that we tend to use exponential functions. So let's go ahead and set up the problem because there is a decay in the problem, right? The problem is a decay type of problem. That means that your rate will be negative. Your rate will be negative. So here is your principal, which is what you start with. And here is your e exponential, natural exponential, raised to the negative 1 or negative r times t, where r is the rate and t is the time in years, and then y is the final amount, right? So in this example, we started with 1 gram, right? That was your principal, and we know that when you pass 5,715, then if you start with 1 gram, that means that half-life you will have half-life in this time. So that means that you're gonna have 1/2 of the substance that you started with. So you take the 1 gram and multiply by 1/2, and that will give you 1/2. So that's how much you have after 5,715. Now we're gonna find R, and our goal is to find R. Now we're gonna use some basic algebra. Remember from last time that if you want to bring down the power, we're gonna utilize the natural log of both sides of the equation. So natural log of 1/2 on the left side, and then the natural log of e to the power of negative 5,715 r. Bring down the power to the front. Sorry, these two will cancel each other out because they're inverse of each other, and so you're left with negative 5,715 r. And then since we're solving for r, we're going to divide both sides by this factor, right? Now we don't have to worry about too much about natural log 1/2. That's just a number. It's just a decimal. Whatever decimal it is, we're not going to stress about it. We're just going to divide this number on both sides, and that's what we have here. There you go. We found r. Now our goal is to find out how much we're going to have when we have 10,000, right, for years. So now that we have found r, all we got to do is replace t with 10,000, and that's what I'm going to do, right? So here you have 1 gram of carbon, right? I put my p, which is 1, times e to now this is negative, right? But you already had a negative there, so negative a negative, right? This negative with this negative will undo each other, and that's why we have a positive value here. So natural log 1/2 over 5,715 times 10,000, and we put this in a calculator, and this will give us 0.297. And then we round it off, and usually I'll let you guys know how much I want you guys to round it off. So therefore we have 0.3 substance of the carbon, right? All right, after 10,000 years. Okay, so that's one application of exponential functions and the natural exponentials. I mean, here we use the natural exponential, but we can also um, we can see cases where we use the other exponentials. All right, so in a similar way, the way we define the way we define other exponentials as a natural exponential, right? You guys remember how we did that over here? How we define a regular exponential as a natural exponential. We're gonna do the same thing with the logarithm. So any logarithm can be written in the form of a natural logarithm. And actually, this one actually applies. This actually